this video, we are going to be doing example 11.7, formation of a neutron star. A star rotates with a period of 30 days about an axis through its center. After the star undergoes a supernova explosion, the stellar core, which has a radius of 1.0 times 10 to the 4th kilometers, collapses into a neutron star of radius 3 kilometers. Determine the period of rotation for the neutron star. The first thing I notice here is that the radius of the star is changing, and then because of that the period of rotation will change. So that implies to me that this is a conservation of angular momentum problem. Now the first thing I'm going to do is I want to find its angular speed. It tells us that it takes 30 days to do one full rotation, so from there we can get what omega is in radians per second. So omega, one rotation takes 30 days. Just do some dimensional analysis here, and you end up that this is the angular speed of the star before it collapses. Now because this is a conservation of angular momentum problem, we want to find the angular momentum before and the angular momentum after. So not only will the speed change, but the moment of inertia will change. So I'm going to find the initial moment of inertia. The star we can model as a sphere. So we'll have 2/5 mRI squared. M will be the mass of the star, which they don't give us. So I'm just going to leave that as m for now and hope it cancels out later. Ri is this 1.0 times 10 to the 4th kilometers, which of course we want to convert to meters. So it would be 1 times 10 to the 4th meters. 1 times 10 to the 7th meters. So we plug that stuff in, and we get 4 times 10 to the 13th m for the initial moment of inertia. For the final moment of inertia, we want to use this final radius here, and again, just m, and we get 3.6 times 10 to the 6th m. So conservation of angular momentum, initial angular momentum equals final angular momentum. So I times omega I, oh, and that should be an F there, sorry, my bad, equals IF times omega F. So let's plug in our numbers from the previous slide. The first thing I see here, once I've plugged in my numbers, is that the m's do indeed cancel out, so I was right about that. Then I will multiply these two numbers together and divide by this number and get that omega f is 24.93 radians per second. Are we done with this problem? No, we are not. The problem asks us to find the new period of rotation. So we know that in 1 second it can go 2.493 radians. So we just have to figure out how many seconds it takes to go a full 2 pi radians. So to do that, we just do a little bit of dimensional analysis and up with 0.25 seconds, which is our final answer. Just want to point out real quick that the star used to be a whole lot bigger, so the period of rotation was 30 days, and now it's so much smaller that the period of rotation is only 0.25 seconds.